So on page 350, we're going to talk about exponential functions, and then the derivatives of exponential functions and the integrals. Now, the natural logarithmic function has an inverse. Like what we talked about in 5.3, it fits all the criteria, so it has an inverse. And its inverse is the exponential function. Okay? So the inverse of the natural logarithm function is the natural exponential function. Remember we talked about how if two functions are inverses, they're reflected in the line y equals x? Well, look there. Okay? This graph you're already supposed to know, right? What the graph of y equals the natural log of x looks like? Well, its inverse, y equals e to the x, looks like that. You need to be familiar with what that graph looks like as well. Okay? So, the definition, the inverse function of the natural logarithmic function, so f of x equals the natural log of x, is called the natural exponential function and is denoted by f inverse of x equals e to the x. You don't have to call it f inverse of x forever. It's y equals e to the x, or f of x equals e to the x. That is, y equals e to the x if and only if x equals the natural log of y. I'm not real pleased with that. Remember what we talked about yesterday, how if f and g are inverse functions, that f of g of x equals x and g of f of x equals x? That works with exponential and natural exponential and natural logarithms. Like so, at the top of the screen. The inverse relationship between the natural logarithmic function and the natural exponential function can be summarized as follows. The natural log of e to the x equals x, that's your f of g of x equals x, and e to the natural log of x equals x, that's your g of f of x equals x. Okay? Why is that true? Because it has to be if they're inverse functions. Okay? That was the definition of inverse functions. These are inverse functions. It has to happen. With me? Okay. Now, what can we do with this kind of thing? Well, we can do a lot of things that are similar to what you did way back in Algebra 1. It's just that the numbers are different. So we can solve 7 equals e to the x plus 1. Okay? And in Algebra 1, like you'd write both sides with the same base, and if the bases were the same, the exponents had to be the same. All right, that's not going to be easy to do on this one, is it? So we're accomplishing the same thing. We're going to do it differently, though. Okay? All right, since we know that natural log and e are inverse functions, then if we take the natural log of both sides, it looks like that. And so then, by definition, the natural log of e to the whatever is whatever. Okay? So the natural log of e to the x plus 1 is x plus 1. And now we don't have any exponents to worry about anymore. We can solve that for x. So we went a different way about eliminating the bases, really. I'm not sure that's what I meant to do, but that's what happened. Okay? And then once I do that, subtract 1 from both sides, and I can either stop there. If it tells me to put it in decimals, then I go ahead and put it in decimals. Okay? This also gives us a way to solve logarithmic equations. All right? Because what's keeping you from solving for x is the fact that x is in a quantity, and that quantity isn't just 2x minus 3, it's the natural log of that quantity. So I can't solve for x until I do something to get rid of that, can I? Well, here's what the something is. In the first example, we took the natural log of both sides. In this one, we're going to what's called exponentiate both sides. We're going to e it. It's the anti-natural law. Okay? So we start here, exponentiate both sides. So that'll be e to the left side equals e to the right side. E and natural log are inverse functions and inverse operations. So e to the natural log of 2x minus 3 is just 2x minus 3. Now I have an equation I can solve for x. If they want an exact answer, give them that. If they want a decimal answer, give them that. Questions? All right. Now, the familiar rules for operating with rational exponents can be extended to the natural exponential function as shown in the following theorem. So, you know how you've always, if you've had two factors with the same base and you were multiplying, you would add the exponents? That still works even if the base is e. And if you were dividing two factors with the same base, you would subtract exponents. That still works even if the base is e. Okay? Now, some properties of inverse functions. In yesterday's section, we learned that an inverse function shares many properties with the function. So the natural exponential function inherits the following properties from the natural logarithmic function. This is due to the definition of inverse functions. So here are some properties of the natural exponential function that we're going to need to know. The domain of f of x equals e to the x is from negative infinity to infinity, but its range is from 0 to infinity. What was the range of the natural log function? That. And what was the domain of the natural log function? That. They traded, didn't they? Okay? So, well, let me finish this. The function f of x equals e to the x is increasing, is continuous, increasing, and one-to-one on its entire domain. It has to be that, or it won't have an inverse. And remember this, since the natural log function was increasing, its inverse has to be increasing. The graph of f of x equals e to the x is concave upward on its entire domain. And the limit of e to the x as x goes to negative infinity equals 0, meaning the line y equals 0 is a horizontal asymptote for x approaching negative infinity. And the limit of e to the x as x approaches infinity is infinity. So there's no horizontal asymptote on the other end. It's going to infinity. So you need to know what the graph looks like. If you got to graph it, you know that you've got a horizontal asymptote here. You know that it crosses, and then it goes up forever. It'd be nice to know where it crosses. Okay? What's 7 to the 0 equal? 1. What's negative 2 to the 0 equal? 1. So what's e to the 0 equal? 1. So when x equals 0, y equals 1. And that's where it crosses the y-axis. Okay? So remember that point, that when x equals 0, y equals 1. Remember that as x approaches negative infinity, y equals 0 is a horizontal asymptote. Remember that as x approaches infinity, so does y. Now, for the fun part. I kind of like that part. I enjoy the eing and the natural logging and those canceling each other out and terrible-looking equations becoming simple-looking equations. I like that. I like this even better. This is the coolest thing about calculus as far as I'm concerned. The derivative of e to the x equals e to the x. That's just awesome. Okay? The derivative of e to the x equals e to the x. Now, there's only so many times they can ask you that without it getting kind of boring, right? Number 1, y equals e to the x. What's y prime? E to the x. Number 2, f of x equals e to the x. What's f prime of x? Well, e to the x. So after you do 100 of those, you get kind of tired of it and you want a challenge, right? So there's a chain rule version because you're not always going to have x as your exponent. You can have an expression of x. The derivative of e to the u is e to the u times the derivative of u. Okay? Like I said, that's kind of easy. So far, so good? Well, I don't know. There's probably a proof of this theorem somewhere. I don't know the proof of the theorem. All right? All right. So, I mean, look, even the authors of the book got excited about it. They used italics. And so even they thought it was cool. Okay? All right. Let's see. Well, if the derivative of e to the x is e to the x, isn't it only fair that the antiderivative of e to the x is e to the x plus c? Okay? So the indefinite integral of e to the x dx equals e to the x plus c. And then the chain rule version. If you have something besides x as your exponent, some expression of x, let that equal u, and then hopefully the du will work out. So the integral of e to the u du equals e to the u plus c. All right, let's see how this works. Number 6 from page 356. Number 6 on page 356. Solve for x. So no calculus really, not yet. We're going to solve for x. And they want it to a decimal, so I'll get a calculator ready. All right, so first off, let's deal with the -6 and the 8. Can't I just add 6 to both sides to get 3e to the x equals 14? Because, I mean, not everything that you've ever learned about solving an equation, we're trying to get x by itself. Well, quite often, to get x by itself, if there's only one term with an x, we'd like to isolate that term. So, we add to both sides. Well, I can further isolate the x by multiplying both sides by 1/3 and getting e to the x equals 14/3. And that's as far as I can get. I can't get x all by itself unless I remember to take the natural log of both sides. So we take the natural log of the left side, that's the natural log of e to the x, and we take the natural log of the right side, so that's the natural log of 14/3. The natural log of e to the x, by definition of inverse functions, is x. Okay, remember f of g of x equals x? That's what's going on here. So the natural log of e to the x is x. So x equals the natural log of 14/3. And if they did not tell us to change it to decimals, we would be done. But they do. So what's your calculator tell you that the natural log of 14/3 is? All right, but it says to 3 decimal places, so 1.540. All right, we okay with 6? All right, number 12. We're still solving for x. This time we have the natural log of 4x equals 1. Well, I can't get x any further isolated without getting rid of that natural log. So exponentiate both sides, e both sides. So we exponentiate the left and turn that into e to the natural log of 4x. Exponentiate the right, turn that into e to the 1. What is e to the natural log of 4x? 4x. Definition of inverse functions. It has to work that way. And e to the 1, no need to call it e to the 1, it's e. Well, we can solve for x now, can't we? Divide both sides by 4. If they didn't tell us to give them a decimal answer, we'd be done. So let's see. I need to get E divided by 4. 0.679, the AP accepts that, even though it's not rounded properly. And if you do round properly, it's 0.680. They don't prefer. I do. I prefer 0.680. I think it's kind of nuts to say you can just ignore everything that comes after a certain digit. But I think they just look at the first 3. I think. As the test gets closer, I'll look that up. Right. And if that's not your final answer, don't round it. It's only once you get to the final answer that you need to round it. Okay? All right, well, let's keep going. Y'all with me? All right, let's do some calculus with it. Number 38. They want us to find the derivative. We have y equals x squared e to the negative x. Well, that's x squared times e to the negative x. This is a product rule problem. Okay? So, the product rule says that the derivative equals the first function, x squared, times the derivative of the second. Now, the derivative of e to the negative x, that's an e to the u problem. It's not an e to the x, is it? It's an e to the u. The derivative of e to the u is e to the u times the derivative of u. So the derivative of e to the negative x is e to the negative x times the derivative of negative x, negative 1. Yeah, that's what we're going to get. But we're going to put the negative sign in front eventually. Okay? Plus the second function, e to the negative x, times the derivative of the first. And the derivative of x squared is 2x. So that's our calculus. The rest is trying to make the answer look as nice as we can make it look. Okay? So the first thing I'm going to do is the negative 1 times the x squared. I'm going to call that negative x squared e to the negative x. And it seems awkward having a 2x behind the e to the negative x, so we'll put plus 2x e to the negative x. Yeah, let's factor, because we don't have to right now, do we? We don't. If the directions say find the derivative, we've done that. But think of all the different things they might ask us to do, okay? Especially if it involves anything where we would have to find critical numbers. We want this thing factored. So let's get in the habit, or let's keep in the habit of doing that, all right? So not only can I factor out an e to the x, I can factor out either a positive x or a negative x. Who knows, right? It doesn't really matter. I factored out a positive x. You could factor out a negative x and then have the inside the parentheses then would be x minus 2. So either way, that I'm not fussy about, neither are the AP people, and I doubt your college professors are either, or college TAs, depending on where you go. Okay? You with me on 38? Any questions? What rule are we going to need to use on number 43? Quotient rule, right? All right, y equals 2 over e to the x plus e to the negative x. Well, let's quotient rule this thing. So that'll be the bottom, e to the x plus e to the negative x, times the derivative of the top, and the derivative of 2 is 0. I kind of like that. Minus the top 2 times the derivative of the bottom. Now, in the bottom, it's the derivative of two different terms, isn't it? So first, the derivative of e to the x is e to the x, and then plus, and the derivative of e to the negative x is going to be, it's going to be negative e to the negative x. It's e to the negative x times the derivative of negative x over the denominator squared. All right, so we've done all of the calculus. Let's simplify. I like that zero factor in front of the negative sign because all that disappears. So I've got a negative in my factor in my numerator. I can factor, actually I am factoring out a -1 and putting it in front. So I've got the negative in front, and then the 2, and then inside the parentheses I did what you suggested and made that e to the negative x times -1 into just negative e to the negative x. Nothing to do with the denominator. And there's nothing to divide out, is there? Those two quantities are close to being the same, but they're not the same. You think maybe sometimes they might be the same and you do need to divide them out? Yeah, that could happen. Well, for instance, if that was a plus sign, then I'd want to do that. No, all I did was take that negative and put it right there. I put it right there. All right, Charlie? Well, you get the first term squared plus 2 times the first term times the second term plus second term squared. So you get e, no, that's not how you make an e. You get e to the 2x plus 2 times, what's e to the x times e to the negative x? E to the 0 plus e to the negative 2x, so you'd get e to the 2x plus 2 plus e to the negative 2x. All right. Well, we got to do some integrals. Come on. 59. Oh, wait. I take that back. We're not ready for integrals, even though I've shown you how to do one, shown you the definition. We're going to do a find an equation of the tangent line problem. Because look, that stuff never goes away. Okay? It never goes away. Sometimes, well, how are we going to find an equation of the tangent line? What's the first step? Derivative. Why derivative? Because that's the slope of the tangent line. Once we have the slope of the tangent line, then we can use our point and get our equation. So, our function is actually an implicit function, isn't it? So we're going to have to be able to do implicit differentiation as well. So we have x e to the y plus y e to the x equals 1. Once we've come up with the derivative, which is our slope, then we'll use the point 0, to get our equation of the tangent line. All right, so to take the derivative, let's start with the derivative of x e to the y. The derivative of x e to the y, we have to use the product rule, don't we? We have to call x the first function, e to the y the second function. So according to the product rule, we get the first function times the derivative of the second. Now, if that was just an x, the derivative of e to the x is e to the x. But it's not an x. It's actually an expression of x, right? Y is our function. So that's a u. Treat it like a u and chain rule it. The derivative of e to the u is e to the u times the derivative of u. So the derivative of e to the y is e to the y times the derivative of y. You see why you got to do it that way? Because y is not a variable, is it? Y is a function. So you can't treat it like you treat x because it's not a variable. It's a function. So that's just the first half of the product rule. Now we have to do plus the second function, e to the y, times the derivative of the first. Now, x is just x. So what's the derivative of x? 1. So what I have underlined in red here is the derivative of what I have circled in red. Everybody follow me? Okay, now, plus, now we have to take the derivative of y e to the x. And we're going to use the product rule on this one too. First function, y, times the derivative of the second. What's the derivative of e to the x? E to the x, plus the second function, e to the x, times the derivative of the first. And the derivative of y is not 1, because y is not a variable, it's a function. The derivative of y is y prime. And anytime you want to write dy dx instead of y prime, that's not a bad idea at all. So, what I have underlined in green is the derivative of what I have circled in green. Everybody still with me? Equals, and then don't forget to take the derivative of 1. Turn that into a 0. Don't leave it as a 1. It's going to mess up your solving it. So derivative of 1 is 0. All right. Let's simplify our derivative as much as we can, or as much as is reasonable. Then we'll substitute 0 in for x and 1 in for y. Little hint, if you're unable to simplify that for whatever reason, could you stick 0 in for x and 1 in for y right now? You could, and then solve it for y prime. I don't recommend that. You could, okay? All right, so let's solve this thing for y prime if we can. So let's simplify what we have. All right, so x e to the y, y prime. I don't need the parentheses around the y prime. Then the x, or the e to the x, y prime down here, I'm going to move that over because I want my two y prime terms next to each other. Okay? So that's all I did there. So ignore the right side of what I have. So all I've done is I've rewritten that without the parentheses. I've rewritten that without the parentheses and moved it closer to the left. Moved it closer to that other y prime term. All right? Now, to save a line of writing, I'm going to do two things at once here. E to the y times 1 is just e to the y. If I'm going to solve for y prime, don't I want all the other terms on the other side of the equation? So I'm going to change that to e to the y, and then I'm going to subtract it from both sides, so it shows up on the other side as negative e to the y. And then the y e to the x, that's simplified nicely. Subtract it from both sides, and it shows up on the other side as negative y e to the x. So you with me on those moves there? A little simplifying and solving as we go. All right, on the left side, those two y prime terms are not like terms. So I can't add those together. So how do I get a single y prime out of this? Factor it. I factor a y prime from those two terms. So that leaves me with x e to the y from the first term, and it leaves me with e to the x from the second term. On the other side, do I need to factor a negative out? I don't know that I need to. I wanted to, so I did. Because, usually the fewer negatives you have, the better off you are. I can't say that that's always the case, but usually. So I factored out the negative, so I just have one negative sign instead of two. All right, to get y prime by itself, last step for solving it, I need to do division. So I divide both sides by x e to the y plus e to the x. So I've got a negative out in front. I've got e to the y plus y e to the x as my numerator. I've got x e to the y plus e to the x as my denominator. And I am done with the derivative. Any questions getting this far? Okay. Now, let's find the slope of our tangent line. What we have so far is a formula to find the slope of the tangent line. We can use that derivative to find the slope of the tangent line at any point on the graph of our implicit function. The point they want us to use is the point 0, 1. So at the point 0, 1, replace x with 0, replace y with 1. So y prime equals negative sign in front. E to the y becomes e to the 1, plus y e to the x becomes 1 e to the 0. X e to the y becomes 0 e to the 1, and e to the x becomes e to the 0. And we remember what e to the 0 equals, don't we? 1. So I've got the negative sign in front. In the numerator, all I have, once I simplify, is an e plus 1. In the denominator, 0 times e to the 1 is 0. So all I have in the denominator is e to the 0, which is 1. Is a denominator of 1 actually doing anything for me? Nope. So that is the slope of the tangent line at that point. So we went from having a formula to find the slope of the tangent line to knowing the slope of the tangent line at that particular point of tangency. Okay? Now, use point slope form. Y minus y1 equals m times x minus x1. So you will replace x1 with 0, replace y1 with 1, replace m with negative quantity e plus 1. So we get y minus 1 equals negative quantity e plus 1 times x minus 0. Well, in that last parentheses, x minus 0 is just x, so that simplifies it a little bit. And then, if they don't tell you what form to put your equation in, in fact, if it's a free response question, you can be done there. But it just kind of irks me. I just have to do that, don't you? I have to. Okay? And now, if they don't tell you to put it in slope-intercept form, you can be finished at either step here. But maybe they do. I don't know why they would. Maybe they do. If they do, then you got to add the 1 to both sides to get that. Or if you were going to graph that for some reason, you would probably want to do that. Okay? Now, are there any questions? All right, here's what I hope you understand. The derivative of e to the x equals e to the x is easy. The derivative of e to the u equals e to the u times the derivative of u is easy. But look, it's still calculus. We're still going to have to use the product rule, the quotient rule, the chain rule. We're still going to have to be able to find derivatives and factor them. We're still going to have to be able to find equations of tangent lines. We still have to be able to find maxes and mins, be able to tell where a function's increasing or decreasing, be able to tell its concavity. Okay? So the fact that the new part today is pretty simple doesn't mean that there aren't going to be any difficult questions. It doesn't mean that at all, because calculus is still calculus. Okay? All right. On page 356, let's do 1 through 18, 25, 33 through 48, and then 49 through 61 odd.